experts and distinguished speakers and participants for taking time out of your busy schedules to support astronomy in Serbia. At Department of Astronomy, we are proud of our alumni. We want to hear their talks and celebrate their success at 19th Serbian Astronomical Conference. Our alumni stand out for their professional accomplishments, contributions to their communities and beyond. We look forward to your contributions and active collaboration during the next days. This opening session is closed, and now we turn over the conference to the chair, Vitor Cardoso, of the first session dedicated to the gravitational waves. It is our great privilege and honor to have as special speakers two giants in investigation of close binary supermassive black holes, Professor Yan-Min Wang from the Institute of High Energy Physics, Chinese Academy of Sciences, and Professor Stephanie Comoza from the Max Planck Institute for Radio Astronomy, both pioneering observational and theoretical investigations of these enigmatic objects. Vitor, you are more than welcome to continue the conference.
Thank you so much. Yes. Let's go ahead, please go.
I think this one.
Hello. Can you hear me?
Yes, perfectly. Please go ahead.
Okay. Okay. Good morning, everyone. Actually, this is in the afternoon in China, in Beijing. Okay. So it's my great honor to have the talk in the Serbia Astronomical Conference. The topic of my talk is observational signatures of a close binary of supermassive black holes, which are really radiating their gravitational waves. So the two pictures I show here is a cartoon for the PTA array to detect the GW, and the right panel is for the residual signal of the pulsar arrival time, published just 1 month ago in September. So this is the really puzzling signals we see so far. So this means that maybe the nanohertz gravitational wave is just a wave to us. It's not farther away. Maybe we will detect the nanohertz GW in next a few years, I think. So the outline of my talk will include a very brief introduction about what is the closed binary of supermassive black holes, and I will show the 10, probably 10, even 11 signatures of binary black holes from observational side. But unfortunately, these 10 signatures are still not enough to detect their binary black hole so far, but I will show you something details. So the last section, I will show the very brief conclusion so far we can have. So as far as we know, the quasar is a very common phenomenon in the universe, which are driven by the mergers or the interaction between the galaxies in the universe. I show here, so this is a very famous galaxy pairs in the universe. If the pair, if the companion galaxy is less than 1/3, this means that the minor mergers. I show you here, the second panels show that probably the minor mergers and left a lot of stellar flows, like in the Milky Way. There are many signatures about the minor mergers in the last 100 million years. And the second, I show so they are very close compared, close pairs of the two nucleus. One is the galaxy from Sloan by Comerford. The separation is roughly 1 kiloparsec, but this is still just a projection distance. And the second is from Stephanie, almost 20 years ago observed by Chandra. This shows the very famous galaxy NGC 6240, but just to show the projected distance, it's 1 kiloparsec. This is really exciting, but they are still not the contact, they are not still the closed boundary of supermassive black holes, because this distance is still so large, and the two nucleus probably still controlled by the galaxy potential, not by the black hole itself potential. So the simulations show the black hole are evolving, driven by the frequent mergers. I show you here from the some simulations. For example, the some seed black holes mergers and then form the massive black holes along the different ways. So today I want to talk about the binary black holes. This means that really close, just before the last stage of the mergers. So the first, I think probably is the first paper to draw attention of the massive black hole binaries. This massive is mean 10 to 6, at least 1 million solar mass black hole in the galactic center. This paper draw that when the merger happens, so the black hole mergers follow the galaxy mergers, but there is a very special phase. The mergers cannot proceed because there is no mechanism to radiating the angular momentum. Basically, make the mergers stop. So this is the very famous final parsec problem. But there are few ideas to overcome such barriers to proceed the mergers to continue. For example, maybe the nuclear star clusters, the star can take away some of the angular momentum. This was already suggested by you from Princeton, but 20 years ago. So there's another idea is probably the dust torus material will take away some angular momentum away, so make the mergers to continue again. So basically, today I'm not interested in the dual AGN. Probably the distance for typical parameters, the distance is larger than 1 parsec. So I focus on the closed boundary with the distance of the less 1 sub-parsec in such a very close distance, because the two black holes control by their potentials. So they are basically the orbital evolution is controlled by, is governed by the GW itself. So what's the signatures? This is I list 10 signatures here, but the most earliest idea for the signatures is the mass density of the stellar distribution of a galactic nucleus. And the X-ray, but not X-ray, X-shaped jet or direct image of the double cores, something we already see some nearby galaxies with double radio cores. And we will have 10 signatures. I will give the very brief summaries and draw your attention. These 10 signatures are still enough. So I will focus on the second 8 signatures, because these signatures allow us to measure the orbital parameters of the binaries. This is absolutely important for the observational test of the nanohertz GW, because of the orbital parameters, orbital period are so long, which is definitely different from a LIGO like 100 Hertz GWs. So this is very important. So in the 1991, 2 Japanese astronomers made the simulation just to show there is a mass deficit in the nucleus. I can show here. So in the center part, so the stars will be ejected by the interaction with the binary black holes. So this makes the nuclear stellar distribution become flat. It's not a cusp. So this is the, however, this is I think it's a very preliminary signatures here. So the 20 years ago, Merritt and Akers suggest that maybe the X-ray-shaped jet in some radio galaxies could be hosted by the boundary black holes. Okay, but we need all of this morphology or the mass density of the galaxy to measure orbital parameters. But unfortunately, this is not so, I don't think this will be feasible to do that. So another signatures related with the radio is from the Kohab and the Merritt. And 3 years ago in Nature Astronomy, they showed the double core from VLBI for the NGC 17247. In this galaxy, they found the 2 cores here. But unfortunately, my colleagues from Shanghai told me they reanalyzed the data with the collaboration with the Kohab and the Merritt themselves. They found the 2 cores disappear. So this is so the morphology are very sensitive to the data. So so basically, the evidence for the boundary black hole is not so it's not so robust. Okay. So the 2 plots now show the LIGO-like GW with the typical frequency to 100 Hertz, but the closed boundary of a supermassive black hole has much lower frequency of the GW. It's basically in the nanohertz because the boundary orbital period is very long. Maybe the 100 years it's very short. The merger time scale for the nanohertz GW is more longer, even 1,000 years, something like that. So this is so this make the detection of the GW, the nanohertz GW, is very different from the LIGOs, because the LIGOs, the LIGOs black hole can merge with 1 second, but the supermassive black hole boundaries merges probably 1,000 years. Maybe the PTA detection only detect the 1 segment or small segment of the GW. They either cannot measure the whole waveform, but also or not the chirping phase, But the LIGO detection can definitely clearly measure the chirping phase. So this makes the detection of the nanohertz GW very hard to measure, to test the GR property from the PTA detections. So this means that we have to think about another independent way to get the orbital parameters, for example, from the optical or even in the radio. So the talk today, I will focus on the optical detections. So the basic pictures for the boundary black holes was done with frequently cited the paper of Artimovis and Loeb in 1996. Basically, they show the title talk of the boundary black holes will clean the center part of the nuclear and the circumnuclear disk, make a central cavity. So, but they also show there is opportunity for the boundary black holes to accrete some gas peeled off from the inner edge of the cavity. So the solitary boundary, each black hole can form its solitary disk itself. They form the mini disk. I show you here. By Bowen did a lot of not only Bowen but also many authors did a lot of numerical simulations. They show there are boundary mini disks around the solitary black holes. This is this is the basic pictures I show here. Let us recall 20 years ago, Luca from Belgrade just to show if their binary Broadland regions, they will show the double peak, or show if the black hole masses are not equal, they will show the Broadland profile asymmetry. You know, that's shown here. This is the typical. But a couple years ago, the two people from Harvard, they show if the black hole binary are evolving at the different epoch, they will show the different profiles. Okay, this means that the profiles from the two binary black holes, that will be very, very complicated, but evolving with the orbital phase. This means that the profile we can see fully depends on the orbital phase, but also depends on, of course, depends on the eccentricity of the binaries. But on the other hand, some simulations show that. So the circumbinary disk have very complicated angular momentum because the clouds will be formed driven by the self-gravity. So the clouds, some clouds could have very strong random motion. So make the binary black holes. So each binary Broadland regions will have the very different angular momentum direction. So basically, the circumbinary disk cannot change the orbital angular momentum, but each binary black hole have a very different angular momentum configurations. Maybe this is by Guyan and Tamara last year, and the last couple of years, they did a lot of simulations about that. So could be the binary black hole really have not only two Broadland regions, but have the third one. This is the circumbinary disk Broadland region. Probably this could be, yes. But the difficulties to detect the binary black hole really, really hard. The difficulties basically is from it itself, because if there are two binary black holes, we just see the very complicated profiles. But on the other hand, we don't know if there are two binaries. But if we see the AGN, if we see some AGNs with a very complicated profile, but we are not sure their content, we are not sure there are two binary, there are two black holes in the center. You know, but the very complicated profiles of AGNs probably indicate the spatially homogeneous or substructured Broadland region are possible in the galactic center. Okay, so this is the difficulties to justify if there are binary black holes in the galactic center. This is I think this is probably the major difficulties to detect the binary black holes in the center. So the first signals, you know, probably the AGN variability, I mean the long-term variability at the scale of a couple of years probably is theoretical. This was suggested by many simulations. You know, I think maybe I just listed the reference, but limited by the sliders. So the reference are not complete, but there is a potential questions. You know, all of the simulations probably just get the peeled gas rate, but this peeled gas rate are not the accretion rate onto the black hole. So probably the peeled gas rate is modulated by the orbital parameters, by the orbital motions, but the accretion rate will be smeared by the viscosity timescale, by the viscosity in the mini disk. So this is very hard to do because the simulations is always limited by the spatial resolution somehow, something like that. But from the observations, there are a lot of data already show some AGN with the periodical long-term variations. I see them. I show you some light curves this is the very famous by Graham in the, 5 years ago. They really show the very, very good, it's a very solid periodical change. But the H beta, unfortunately, showed a very symmetric. But the narrow part, the narrow component of the H beta opposite with the broad component. I show you here. This is the H beta profile of the PG 1302 minus 120. This is the PG quasars. So the Catalina also showed the other monitor more than 10,000 AGNs in the last 10 years. They show roughly 100 AGN probably have the long-term periodical variations. But unfortunately, if we really test how robust the periodicity with this AGN, it's really I think the probability by the random, by the damped random walk could be large. Maybe just you know, the opportunity are roughly about 1% if we really test the periodicity. So I show you here some more the so-called periodical changes in August anyway. So I think that most of them could be pseudo-period. I'm sorry to say that, but they really show the very debate for the periodicity. So they're only from the long-term variations. I think it's really, really hard to get the signals of the binary black holes. But what we can see details if there are two black holes. I think Guyen and Tamara did a lot of work in the last couple years. They show very complicated profiles. The double peak or triple peak with even multiple peaks here. So really, really complicated. But this they also limited their calculations for the circle orbit. But on the other hand, if there are binary black holes, probably the double peak will have periodical shift like the binary stars. I show you the cartoon. It's very, very easy to understand. So the blue peak and the red peak probably is changing with period, something like that. But it's not really easy to do from the observational side. Oh, okay. So the first signals from the very famous AGN, this was done by Andy a couple years ago. This 4151. They show the radial velocity just looks like the spectroscopy binary stars. They show the H beta profile can be decomposed to two components, which corresponding to the two binaries. Looks like that. But the question is, it's very obvious. The decompositions could be not unique due to the multiple components. But on the other hand, another famous two AGNs, NGC 5548, another European 120, show something similar to NGC 4151. We can see the light curve, the continuous light curve shows some periodical change, especially for the European 120. It looks like the blue and the red peak really are changing with kind of a period of 30 years for the for NGC 5548, but 20 years for a Rockland 120, like that. So there is a large campaign to monitor the quasars selected from Sloan and other AGNs for a systematic search for the closed binary to monitor the radial velocity variations. This was suggested by Heracles from Penn State. This just to show the opposite of the double peak will change, looks like this. But the latest result can be shown here. It looks like the follow the theoretical expected like curves, but such a campaign, I think, probably need another 10 years. So a couple of years are not enough. So this is the disadvantage of the monitoring the opposite of the broad component looks like. So on the other hand, if we monitor spectroscopically monitor the candidate of barrier black holes for the reverberation mapping campaign, this could be more efficient. You know, oh, sorry, this is the it's 1992 year. It's 1992. Blandford and McKay derived very details the transfer function from the light curves. Basically, they suggested to do for the black hole mass. So if there are two black holes with two polar regions, if we see the cartoon here, if there are two binary proton regions, we can get, if we recast the 2D transfer function, just to follow the Blandford and McKay, we can get the composed 2D transfer function by the individual black holes. Looks like that. The parameter gamma 0 is kind of a parameter related with the mass ratio or the light curve ratio, something like that. If you are interested in see the paper in the details. So let us compare if there's a single proton region, or if there are two binary regions. We see the 2D transfer function are really different. The difference are caused due to the orbital motion. This is the the blue shift and the red shift. So this also due to the Kepler rotation, something like that. So another signals we can see probably from the gravity. This is the instrumentation on the VLT interferometer. They measured the center of the photons. So basically they can get, if there are two black holes or two proton regions, we can see the differential phase are very different from the single proton regions. So we think about the four simplest configurations like here. But see the details in the very complicated configurations, the Angekas paper this year. So another signals, probably this is the recent paper from my group. So ARMA basically has very high spectral resolution. In the NGC 1068, they just detect the counter-rotating disk within 7 parsec. So the smaller disk inside, just 2 parsec, is rotating with the counter direction with the auto part. So this cartoon show here, if the system exists for longer time, but for example, it exists for 10 to 7 years, so the Kelvin-Helmholtz instability will totally destroy such a configuration. So, but however, the ARMA detected the two counter-rotating disk with the Kepler rotation. They really get the very good data. So this means show that the unique solution for such complicated counter-rotating disk is the binary black holes. So the tidal torque from the binaries will supply the angular momentum to the inner part. So keep the rotation is the counter to the outer part. So this is the really exciting new kind of evidence from the radio observations for ARMA. So the people from the Japanese group, they're looking for more data from the ARMA to search their counter-rotating disk if this situation is popular in the Cipher-2 galaxies, or the NGC 1068 is just a special one or not. So this we will see the data in the future. I think see the more data in the future. So the Savage and Luca show the polarized spectrum for the several configurations. If they are separate Brodel regions, maybe show their profile with the double peak, of course, and the sorry, maybe the plot are not enough, but here show that the polarization angle is kind of the wave, is a kind of a function of the wavelengths, and the polarization degree also is kind of the wavelengths also. They show that the first case is separate, and the second is partially merged with the carbon envelope, and the model C just to show the merged one, and case D with not disk with the two spirals. They show very different. But the question is, what is the scattering configuration can be determined by observations, not only by the model. So this is the simulations show here, but we are really looking from observational data from Lucas group. So a couple days ago, I showed something, maybe crazy idea. The changing look AGN could be the binary, could be candidate of the binary black holes. You know, the changing look AGN was discovered in 1980s by chance. Some AGN at the beginning showed the type 2, type 1, but they suddenly changed the type and changed into the type 1, type 2, but with this very short time scale. So the left panels show the very typical the changing look agents from Sloan data. They show at the beginning, they show the very broad H beta component, but the broad component will totally disappear in couple of months or 1 year, something like that. So the question is very obvious. You know, the no theoretical model can explain such a phenomenon according to the classical model of accretion disk. The heating and the cooling front has much longer time scale than the observed of changing look. So this is the very serious challenge to the what is the engine of the changing look AGN in recently years. You know, so the right panels show that some typical time scale of the standard accretion disk models. So basically, this cannot match with the theoretical model here, or with the observations. Yeah, but on the other hand, you know, if the internal mechanism cannot work for the change, cannot operate the changing look, but what is the external? What's the external mechanism in the center? But I think probably the second binary black hole will have very strong tidal torque acting on the mini disks, right? This means that we are removing the angular momentum of the mini disk, and all the transfer some angular momentum to the mini disk. So basically, the accretion will be quenched. So if the accretion quench, ionizing photons will be we're not able to photonize the existing Brownian regions, so they become the they have to change look at the pericenter part of the orbital. But when the secondary leave the pericenter and then the type 2 aging will gradually change into the type 1. The Broadland region will be seen again. So this is, of course, this is only speculation. We need a long-term monitoring campaign to see if the changing look aging also periodical for this case. But I remind of you, the changing look happens probably doesn't exactly follow the variations of the light curves. So see some details with the paper in the archive. So there's a long-term campaign with Wyoming University Observatory Telescope. We called the MAHA, basically mean that monitoring AGN with H-beta asymmetry. So we already continued the campaign for 4 years already. So the MAHA target mostly focused on the H-beta with very symmetric profiles. So the observation already large for the, so we hope to have the more than 3,000 hours per target. And now we already, the sample is more than 80 AGNs, but we already have very high quality light curves already. The goal is to select a candidate from the MAHA target for the, for example, for the VLT for gravity observations. So if the boundary I show here again, if the boundary exists, we see complicated profiles. If we do the real-world mapping campaign, we will see complicated 2D transfer function. If we observe them with gravity signals, we will see the more complicated signals here, but also see the paper more complicated configurations and results from Angelica's paper. So if we select some best candidate, we probably to try to apply the observation with gravity with the highest spatial resolution to see if there's some gravitational wave, see something there. So just a couple weeks ago, the ZTF found the EM counterpart of gravitational wave, LIGO gravitational wave with the Sloan quasar. This recall me back to our paper 20 years ago. We just suggest the quasar accretion disk probably host the stellar binary black holes in the accretion disk, because we know the Broadland region is very, very metal rich. So their internal star formation cannot be avoided. So probably the starburst and the triggers of supermassive black hole activities will naturally lead to the mergers of stellar black hole binaries. So so this is the really interesting results from LIGO recently, the GW900521. They found the remnants, the mergers, the remnant of BH is 140 solar mass. The gravitational waves take 9 solar mass away. So fortunately, the ZTF found the host with the typical quasar spectrum here. The light curve shows so beautiful. The color doesn't change during the mergers. So there is the outburst of the GW papers to discuss the quasar can host the LIGO GWs. So this is my conclusion, very brief conclusions here. So the closed binary of supermassive black hole are still elusive in observations. But we are continuing to work hard, try to find the signals which are still not enough. So basically the question is, what's the final criterion to detect the binary black holes, supermassive black hole batteries? So before GW detection or after the GW detection, we don't know that. So what is a robust way to measure the orbital parameters to test the GW properties? I think in the future, maybe the reverse mapping along with the gravity with the VLT interferometry can be done, this for sure. Thank you for your attention. That's all.
Thank you, Jianming. This was a wonderful overview. Thank you so much. I think we have time for one quick question. So if there's somebody who has a pressing question, please go ahead. Okay, I don't think so. But so I would suggest, in any case, that after Stephanie's talk and before the coffee break, we see again if there's any related question.
We have one question.
Oh, yeah, go ahead.
Yeah, we have one question.
Okay, go ahead. What's the question?
Eddie?
Oh, you're very faint. No, let's proceed. I think right now you're very faint. I would suggest that if there are questions, please write them on the chat. And then after Stephanie's and before coffee break, we look into that.
Yes, it's a very good idea.
Yeah. Thank you so much.
Thank all of you, my friends in Serbia. Okay.
Thank you.
Take care in such a crisis of COVID-19 pandemic. Take care.
Thank you. Okay. Bye-bye. We now proceed to Professor Stephanie Comosa. Stephanie, please go ahead.
Okay.
Okay, getting ready to share screen. Okay. Okay, can you hear me?
Perfectly.
Okay, excellent. So first of all, I'd like to thank the organizers for inviting me to give this talk. It's really a great honor and a great pleasure talking about this topic at this conference. Now I'm going to give an overview of the observational evidence for supermassive binary black holes, which has become a very active field of research in recent years. Now, why are we interested in this topic? Jianming Wang has already nicely introduced several facets of this topic. Now, first of all, hierarchical models of galaxy formation do predict that binary supermassive black holes should actually be common at the centers of galaxies. Secondly, galaxy mergers trigger quasar activity. That's an idea that came up in the 1980s, that interacting systems and mergers host luminous quasars. And in fact, in recent years, there has been ample observational evidence that the most luminous quasars are in galaxy mergers. Now, this is interesting because quasars are the major sites of black hole growth, where a large amount of accretion is taking place, where a lot of feedback is taking place, and this system drive the galaxy black hole scaling relations. Then, of course, we all know that the coalescing binaries are the most loudest sources of gravitational waves, which will be detectable with future gravitational wave missions, especially the LISA space-based interferometer. And As these two black holes coalesce, the gravitational waves take away linear momentum, so the newly formed single black hole will actually recoil. It receives a kick velocity. According to recent numerical relativity simulations, these velocities in rare cases can be up to a few thousand kilometers per second, implying that there should be galaxies without black holes at their centers. Now, there are several key stages in the evolution of galaxy and black hole merging. First of all, it's the merging of the galaxies themselves by dynamical friction. The two black holes will sink to the center of the potential up until separations of about 1 parsec, they start to form a bound pair. And a lot of theoretical attention has focused on this particular phase of the evolution. The early key question has been, is there enough interaction of the binary with its surrounding, with gas and stars, to carry away momentum and energy so that the orbit will shrink to a compact stage, typically 0.01 parsec or less, where then gravitational wave emission takes over and drives a rapid coalescence of the binary, and in some cases, the newly formed single black hole might then recoil. Now, studying pairs and binaries of black holes at all stages of merger evolution is of great interest. For instance, we'd like to know when does accretion set in the course of a galaxy merger? Is typically just one or both black holes are active? How fast do the supermassive black holes grow? How fast do they coalesce, and what is the coalescence rate? And of course, we'd like to know how frequent they are recoiling black holes and what is the distribution of their kick velocities and amplitudes. So in this review, I'll distinguish between wide supermassive black hole pairs. These are large separation systems which can be still spatially resolved, but they are at wide separation. While secondly, there's a compact supermassive binary black holes. They are much more evolved, tightly bound to each other. However, in all these cases, we rely on indirect signatures to actually detect these systems because they are spatially unresolved. These indirect signatures are generally some kind of periodic signal in one way or another. So let me briefly start with the wide supermassive black hole pairs. Now, one challenge in identifying them is that the gas-rich galaxy mergers, which power the accreting supermassive black holes, they have a lot of gas and dust in their centers, and it's not easy to actually observe their very course. However, hard X-rays are very powerful, detecting even highly obscured accreting supermassive black hole systems. And a prime example of this is the galaxy merger and ultraluminous infrared galaxy NGC 6240, where here in this optical image, we can see the conspicuous loops and tails, which signify a past merger. And a lot of attempts have been made to peer into the very center of this galaxy in the optical near infrared. However, it was never possible because large amounts of gas and dust in the very center of this galaxy. However, then when the X-ray Observatory Chandra started operating, which allowed for the first time high-resolution imaging and spectroscopy in X-rays, it detected not only widely extended soft X-ray emission due to starburst activity, but two luminous point sources in the very core of 6240. X-ray spectroscopy led to the detection of two characteristic ion emission lines, and alpha emission lines, which are the telltale signature of AGN. So the system harvests two accreting supermassive black holes, which are at a separation of about 1 kiloparsec. Now, we've also used Chandra to observe a much larger sample of luminous infrared galaxies like NGC 6240-like. We detect a lot of structure in the core, including multiple point sources. However, all of these cases are more distant than 6240. And the quality of observations is not yet good enough to distinguish between, say, nuclear starbursts and AGN. However, the fact that this nearby system shows a binary suggests that there's many more of them in the population of LIGs. Another wave band which can penetrate gas high column density is the radio band, and this has been used to search for binary black holes. And the best observed case is this one, a radio galaxy of 402, which does not only show extended radio emission in the form of jets, but two compact cores, compact variable flat spectrum cores, which are interpreted as two separate supermassive black holes. These are separation of 7 parsec, one of the most compact systems spatially resolved. Now, thanks to large spectroscopic surveys and databases which have become online in the last number of years, for instance, the Sloan Digital Sky Survey or LAMOST, a lot of effort concentrated on searching for wide supermassive black hole pairs in the optical regime. And here the key idea is to search for optical O3 double peaks. Here you see the typical part of an optical spectrum. All AGN do show bright emission lines, for instance, from oxygen-3. These are usually single peak, and they arise from the narrow line region in AGN. So we see here a sketch of the AGN central region. We have the black hole, the accretion disk, and the luminous emission from the accretion disk is reprocessed by 2 emission line regions, the broad line region, and at larger distances, the narrow line region. So the idea is, if we have 2 nearby galaxies, perhaps in the process of interacting or merging, we should see double peak to 3 emission. And in fact, a large number of these systems have in fact been selected from the spectroscopic databases. The one complication which has then emerged, that there is a number of alternatives which only need a single accreting supermassive black hole, a single AGN, to produce double peaked 3 emission lines. These are two-sided jets or outflows or rotating gas disks. We can have a single AGN ionizing the interstellar media of both galaxies of the merger. And as shown recently, we can even have artifacts, seeing-based artifacts, which cause light spillover into neighboring fibers, so that O3 appears to be double peaked, but actually is not. So selecting double peakers is a first important step, but then imaging spectroscopy is needed to pre-select the true pairs among them. And this has been an active field of research in recent years. Here you see an example to the left of optical images of some of these O3 double peakers. Indeed, you can see there's 2 galaxies involved in the merging, but only radio observations in one case pinned down the pair. In this case, detecting 2 bright radicals, both of them almost radio loud, in the system which is at 7 kiloparsec separation. Now, all of these systems are at wide separation. The advantage is that we can spatially resolve the 2 accreting black holes, but we also, of course, like to detect the compact evolved systems. Now, in all of these, rely on indirect signatures of actually identifying them. And so most of the binaries are actually candidates which have to be confirmed. Now, a number of different signatures have either been used or predicted to search for these binaries. Most of them make use in one way or another of periodic phenomena. Then, of course, next we have the coalescence of the 2 binaries. We expect the loud gravitational waves, a very intense field of study right now is also to check for and predict electromagnetic signatures which appear quasi-tenuous to the gravitational waves, which also would allow to pinpoint at high spatial accuracy the actual counterpart to the gravitational wave source. And we can also search for binaries by identifying their post-coalescence signatures. This has been suggested, for instance, in form of typical structures, characteristic structures in radio galaxies, like double-double radio galaxies, which have an interruption of their accretion phase, and then they start launching the jet again, or by the identification of candidate recoiling black holes, which imply that the coalescence must have happened. Now, in my talk, I will not talk about coalescence and post-coalescence, but will summarize some multi-wavelength studies of pre-coalescent supermassive binary black holes. Now, an idea which came up early in the seminal paper by Begelman, Blandford, and Rees was to look at the structures in radio jets of blazars and radio galaxies. A number of them, they show characteristic bands and S-shapes or other wiggles. And they also suggested that these might actually be the effect of the presence of a binary black hole. And so a number of these systems actually emerged. So a number of radio galaxies show characteristic deviations, semi-period deviations of a jet from a straight line. For instance, Macayan 501 is a very well-known example. PKS 0637 is another remarkable example. Now, the idea in explaining these structures is that we have a modulation either due to the orbital motion of the jet emitting secondary black hole around a primary, or else that we have a precession of a jet which periodically sweeps our line of sight. However, we must also keep in mind that alternatives still exist in interpreting the systems, like helical magnetic fields and instabilities in jets. A very remarkable observation in the radio regime, employing a new technology, a new method to search for binary black holes, was this case of 3C66b. This is a nearby giant radio galaxy, and via the eye observations, making use of a second source nearby, a point source fixed in position, to measure at very high precision the spatial motion of the foreground 3C66b, and that led to a detection of periodic shifts in radio position at a period of about 1 year. Now, the interpretation of this was that we are seeing the elliptical orbital motion of a binary black hole with a primary, which could be as massive as 5 to 10 to the 10 solar masses. Now, this system is also interesting because a large part of the initial parameter space for the black hole masses in the system could be excluded by pulsar timing constraints. An initial work by Janet et al. Suggested that the primary black hole mass must be less than 7 to 10 to the 9 solar masses. Of course, pulsar timing constraints have become better in recent years. They can be more restrictive on the mass of the black hole. So they allow to exclude a large part of the parameter space, but not yet all of the parameter space. However, two important points here. First, this radio method itself is very powerful of directly detecting orbital motion of binaries. It will be interesting to point to more sources. And secondly, since 2015, actually, pulsar timing array results have started to constrain binary black hole populations and individual systems. Now, already introduced by Jiaming Wang, a few percent of all quasars do show not single peak, but rather double peaked optical broad emission lines. An example is shown here for H alpha. And one early idea by Martin Gaskell was that these systems might present binary supermassive black holes where gas clouds bound to each black hole produce their own broadline region signal. And then as these two black holes revolve around each other, the red and blue peak of this double peaked emission line should show a systematic shift. This is a very strong prediction, and at least some of these systems should show variability, spectroscopic variability on the time scale of years. However, then the first systems which were looked at, they never had the expected orbital motion. And so for these few systems, it was concluded that processes in the outer warp accretion disk around a single black hole actually cause a double peak profile, Recently, two important progresses have been made. First of all, the Sloan Digital Sky Survey has allowed to select large samples of these optical broadline double peakers to be monitored for long times, searching for candidates which show the predicted orbital motion. But even more importantly, there is a number of nearby well-observed AGN which have already been monitored for decades. And especially my Serbian colleagues have played a key role in this field of research. And the first such example of a very well-monitored AGN, the well-known NGC 4151, based on 43 years of data, has shown a periodicity signal in its flux light curve, but also in a particular component in its broad gamma emission line. And Adibon and collaborators have shown that the system can be well explained by binary supermassive black hole with eccentric orbit with a period of 16 years. This has become a very important new field of research, following two aspects. First, searching for other systems which show this signal in their broad lines and making broader theoretical predictions how reverberation mapping of broad emission lines should appear in binary supermassive black holes. Our conference chair and Jelka has, for instance, worked a lot on this important topic, and Jiaming Wang actually in his talk summarized this very well. Now we can also look for semi-periodic continuum variability. This has been done a lot in blazars, especially in the optical band, but not only in the optical band, but also in X-rays and gamma rays, where periodicities have been detected in the long-term light curves of blazars. And the longer periodicity timescales on the order of months to perhaps decades have often been suggested to be linked to the presence of a binary supermassive black hole. Now, one very well-observed case is PG 1302. And you can see its light curve here. This was selected from the Catalina real-time transient survey among a large number of sources, and has shown a periodicity of about 5 years. A lot of follow-up work has then been done on this remarkable system, and one early idea was and is that the light curve is actually driven by a jet precession in a supermassive binary black hole at subparsec separation, where the jet periodically sweeps our line of sight, and then you see peaks in the light curve due to Doppler boosting. Now, and many more potentially periodic systems, not only blazars, have recently been selected thanks to the excellent transient sky surveys which are currently ongoing. What we actually have to keep in mind, though, is that there's a number of cases where the periodicity then has no longer been seen in follow-up observations. And so sometimes it has been suggested that we could have chance variability or noise. So independent confirmation of these candidates is needed either by long-term monitoring or in fact by combining different signatures, like looking simultaneously at the structures of the radio jets, at the continuum variability, and at the broadline variability. And that has been started to be done in recent years. Now, next, I would like to talk about the one blazar among the periodic variables which has the longest covered light curve, which has the densest multi-wavelength monitoring, and which also in fact has seen the most detailed orbital modeling. And this is blazar OJ287. Now its light curve, its optical light curve displayed here, goes back to the late 1890s. Of course, at that time, the system was not known. It was not known that it was extragalactic at all. However, we can use this photographic plate archives, which exist around the world, to reconstruct its long-term optical light curve, also because it is actually such a bright source. If you look closely at this light curve, then the outbursts seem to repeat. From 1970 on, the light curve has seen a dense coverage, and they seem to repeat at the periodicity of about 12 years. And further, each of these outbursts, if you zoom in closely, is not just single peaked, but double peaked. Now, a number of different models have been suggested to explain this light curve, all of them concentrating on the presence of a binary supermassive black hole in this blazar. However, different variants of binaries have been initially considered, and now by far the best explored model with the most simulations and the best record of making predictions and confirming them is sketched in this artist's image here. So the idea is that we have a secondary supermassive black hole, which is orbiting a primary surrounded by an accretion disk. And we see these bright flares whenever the secondary impacts the accretion disk around the primary. Now this model then makes two main predictions. One is the presence of impact flares once the secondary hits the accretion disk around the primary. And the second prediction is the existence and timing of after flares, which arise when the impact disturbance has traveled to the inner accretion disk and then causes enhanced accretion event and jet activity in response. Now, the physical picture for the impact flare is actually based on hydrodynamical simulations of Ivanov et al., who looked at the impact of a black hole onto an accretion disk, which this collision triggers a supersonic two-sided outflow. These bubbles then expand and cool. Finally, they become optically thin and emit thermal Bremsstrahlung, and that is when we see these flares. The second pillar of this binary black hole model is the actual two-body orbital modeling of the two black holes. And this has been done with great care by Waltonen and collaborators who calculated Keplerian orbits with 2.5 post-Newtonian corrections. And they concluded that the observations are well modeled with a binary black hole with a very massive primary of 10 to the 10 solar masses, a secondary which is about a factor of 100 less massive, in a highly eccentric, highly precessing orbit with a semi-major axis of about 10,000 AU. Also, these authors reported tentative evidence for orbital shrinkage due to emission of gravitational wave based on the timing of the peaks. So if this confirmed, then this actually may make OJ287 the only multi-messenger source which is detected before the actual detection of its gravitational waves. So clearly it's a very interesting system to study. Now, the last of these impact flares was predicted to happen in 2019. And of course, an important question is, did we observe it? And the challenge at that time was that OJ287 is an almost ecliptic target. So once each year, it's projected very close to the location of the sun. And then for 2 months, it cannot actually be observed ground-based. Unfortunately, the prediction for the 2019 impact fell in one of these windows, unobservable windows, where also a number of space-based telescopes could not observe it. However, the Spitzer, the infrared observatory with its different orbit, could observe OJ287 in the time frame of the predictions, and it detected an infrared flare within 3 hours of the predicted impact flare for the binary black hole model of OJ287. This was also, by the way, one of the last observations ever carried out with the Spitzer Observatory. Now, while historically OJ287 has been mostly monitored at optical wavebands, and there's dedicated ongoing dense coverage to continue following OJ287 in the optical band, we have started a dedicated multi-year monitoring campaign of OJ287 with a Swift X-ray observatory, which also has a UV telescope on board measuring 3 UV and 3 optical bands. This monitoring started after the last optical high state in December 2015, and we have by now achieved the dense coverage of OJ287 in multiple bands, recording various interesting states, spectral and flux states of activity. And incidentally, this afternoon there will be a press release at 9 a.m. Pacific daytime. However, for instance, we recorded a very deep flux minimum labeled here in light blue, and this could be used to trigger follow-up optical imaging in order to detect the host galaxy, which has been challenging to actually record because of the bright glare of the blazar. However, in particular, what I'd like to highlight here is a discovery of a bright outburst, one of the brightest in X-rays ever seen from OJ287 in April to June 2020. And during this outburst, right at its maximum, we were able to trigger follow-up X-ray observation with the XMM Newton mission up to 10 keV and with the New Star mission up to 70 keV. These X-ray observations led to the detection of a new, very strong, soft X-ray emission spectral component, which can be well modeled by synchrotron emission. And also there's multi-wavelength observations which similar point to a synchrotron flare in the form of quasi-simultaneous multi-waveband variability, the detection of a radio flare with the Effelsberg telescope, the detection by Solar et al. Of high polarization during this April to June 2020 flare. And so we've likely witnessed here the launch of a new jet component. Now the timing of this outburst coincides with the predicted after flare, which should be occur after the 2019 impact flare has been observed. Now, there's multiple ongoing and future observations of the system, as with multi-waveband monitoring will continue. With Effelsberg, we are recording the radio flares and multiple frequencies. At this deep optical UV low state, we obtain new host imaging of the blazar, and perhaps particularly interestingly, there is future and scheduled radio observation to observe OJ287 at the highest spatial resolution, including with the Event Horizon telescope. And as a note in passing, this would be the only observation where we could have a chance of just detecting or spatially resolving the primary and secondary black hole, but of course only if the secondary black hole is also a radio emitter. Now, OJ287 will not be a source emitting in the laser sensitivity range. However, it is in the pulsar timing array range, not yet detectable, but there's prediction that it will become detectable in future PDA observations in the SKA area. Now, let me spend the last few minutes of my talk in addressing another type of binarity and another type of signature of binary black holes. Now, first of all, of great interest with respect to gravitational wave detections are so-called MRIs, extreme mass ratio inspirals, which consist of a stellar mass point source inspiraling onto a supermassive black hole. These will be in the laser sensitivity range in the range of space-based gravitational wave interferometers. Now, if a solar type star was inspiraling on a supermassive black hole, then the gravitational waves would only be detected if the event happened in our own galactic center. However, of special interest are compact stellar end states, especially white dwarfs, inspiraling onto supermassive black holes. And this is because they would simultaneously give us a gravitational wave signal and an electromagnetic signal, allowing a great localization of the sources. Now, why do we expect an electromagnetic signal? Well, this is because stellar tidal disruptions happen. So once a star approaches a supermassive black hole too closely, It will feel the increased tidal forces of the black hole, and ultimately, once the tidal forces exerted by the black hole exceed the self-gravity of the star will be tidally disrupted, and then part of the stellar debris will be accreted onto the supermassive black hole, producing a luminous flare of electromagnetic radiation. Now, these systems have been observed in recent years, and typically the X-ray or decline light curves in other bands are characterized by T⁻⁵, a relatively smooth T⁻⁵ decline law, as shown by this solid line in this plot. This is because the stellar material is distributed on a number of different Keplerian orbits, rapidly circularizes and discretes around the black hole. However, in one case of such a stellar tidal disruption event, we observed a very unusual light curve, not smoothly declining, but showing repeated dips and recoveries. And this was actually reminiscent of earlier theoretical simulations by Leo et al., who looked at stellar tidal disruption events under the presence of not a single black hole, but rather a binary black hole, where the secondary black hole temporarily disturbs the accretion stream on primary, then leading to characteristic phases of dipping and recovery in the light curve of these events. And detailed simulations by Liu et al. Have then shown that indeed this tidal disruption event observed in X-rays, its light curve is well modeled by a milliparsec supermassive binary black hole that can explain the light curve well. Now, there's a number of implications then. At sub-milliparsec, this is one of the most compact systems known. Of course, it has overcome the final parsec. Like the majority of the other compact binaries I introduced before, it will continue to shrink due to gravitational wave emission. This one would then be in the LISA sensitivity band. Now, what I'd like to highlight here in particular is that this is currently the only method of detecting supermassive binary black holes in quiescent galaxies. Now, we have heard a lot about the signatures of searching for binary black holes in active galaxies. And usually you need at least one black hole to be active in order to detect the binary. Now, there could be many quiescent supermassive binaries in nearby galaxies, and we would basically have no way in detecting their presence, except for our own galactic center, where our spatial resolution would be high enough to search for such a supermassive second black hole based on stellar orbits. But in all other quiescent galaxies, we would have no way detecting it. And so using tidal disruption light curves is a nice way of searching for supermassive binaries in quiescent galaxies. So far, a second candidate has emerged. We are working on a third one. There's prediction that up to 20% of the TDEs could happen in binaries, also because in the course of the binary evolution, there's phases where the tidal disruption event rate is actually enhanced. And now we need a dedicated mission with well-covered light curve to identify tidal disruption events, but also then have well-covered light curve to search for the characteristics of binary black holes. And one such mission will be the Chinese mission Einstein probe, which is currently under construction. And one of its key missions is to identify new TDEs and to identify electromagnetic counterparts to gravitational wave sources. So that will provide us with a lot of new interesting results on transients and TDEs and binary black holes in particular. Then there's the next generation of giant optical telescopes, which will provide us with exquisite detail of the imaging and spectroscopy of galaxy mergers. And of course, we all look forward to the first detection of gravitational waves once the Space Interferometer LISA has been launched. And I stop here and thank you for your attention.
Thank you so much. This was a really fantastic overview. There's at least two questions. One is in the chat. I'll just read it. It's from Eddie. And the question is the following. There is an archive paper from you actually about OJ287 where the host is examined. And the question is the mass of OJ in agreement from the, when you get it from the host estimates and from the binary black hole orbit?
Yes, so this is a very good question. It has been attempted to study several times. And the one key challenge is that the blazar is usually so bright that it's very challenging to detect the host well and to detect the faint outer parts of the host well. So our most recent paper was based on this very deep optical low state I mentioned, where we tried to use a chance of obtaining a host image then when the laser glare was least disturbing. Unfortunately, OJ287 did not fully cooperate, and its emission was already rising again when we took the host image. Now, there's 2 points. If we just measure the central part of the host, which is well detected, then its mass is below the scaling relations, such that then the OJ287 mass would have to be over massive. However, we are missing faint outer halos of the system. We would need deeper follow-ups to measure the full host galaxy to make a precise comparison.
I see. Actually, I also have a question regarding OJ287.
Yes.
So you mentioned that the Event Horizon Telescope could measure the smaller black hole if it emits. Is there any reason why we would expect there to be emission from the smaller?
Yes, that is a very important question. So there is predictions that once the secondary impacts the disk on the primary, a lot of gas is ejected from the disk, and based on the initial simulations of Ivanov et al., we do expect some temporary accretion onto the secondary black hole then. So if we are lucky to catch it at that phase, and also if that accretion event does trigger a temporary jet, then and only then we'd be lucky to actually have a chance to measure it.
I see. Very good. Any further? I think we have 2 minutes for one last question before we break. Any question?
Yes. Could you hear me?
Yes.
Yes.
Hi, Stephanie. Nice. Thank you for very nice talk you gave.
Thanks.
And it is very interesting, of course, to see about closed binaries, especially. Can we expect some example in the case we have some candidates that they are in optical part? Can we expect also the radiation in radio for those candidates? And can we match radio and optical to find some good candidates for supermassive black hole binaries?
Mm-hmm. Yes, that's a very important comment. Indeed, whenever we see the optical variability, and if it does come from a jet, we should also see the signal in the radio. And indeed, combining them would be more powerful than using just one waveband. Now, the challenging for radio light curves is that they are much less well covered than the optical light curves. For the optical light curves for the bright systems, we could even monitor them ground-based, or for radio, we might have a data point every few weeks. But then, of course, the other question is whether we could use radio imaging, highest resolution radio imaging, to search for the binaries. That will be a very important application. It depends on how compact the system is, whether we have a chance to detect it in the radio VLBI or whether we don't. But it will be a very important approach, yes.
Thank you.
Okay, thank you so much. I'd like to thank both the speakers, Stephanie and Jianmin, for the great talks. And I think now we should go for a coffee break. I don't know if the organizers want to add something. No, I think we
Victor, can you hear me?
Yes, perfectly. Yeah.
I'm sorry, I was on another microphone. I think that we have some comments and questions for Professor Ian Min as well in the chat.
Yeah.
From Professor Alexander Zakharov.
Oh, that is correct. I think that Professor Min answered them on the chat, but perhaps there are some comments that you'd like to address to all of us.
To all participants once again, or it's okay. Okay, So this is actually the end of this session.